Alright, this is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our ATV Experimenters Night. And have we got a show for you? I have sitting next to me Rex Moncur VK7MO, who very recently, a week ago?
Yes,
exactly. A week ago exactly. There you go. Whilst we were playing in the ATV studio, Rex was freezing up on Mount Wellington, making extending or gaining back.
Yes.
Gaining back. Sorry, I've got to get that right. Gaining back the 24 gig Earth Moon Earth world record back to VK7. So I'll hand over to Rex, and Rex has a PowerPoint presentation sitting here waiting for me to do some vision switching on, and so over to Rex.
Well, thanks, Justin. We might just go straight to the PowerPoint presentation. Whoa!
Let's change that. Sorry.
I disappeared.
Okay, go for it.
Well, where's it going? What there's going out,
Yes,
is it?
that's
Thank you.
Yeah.
Okay, here's an image of the Earth with my station in Tasmania, G3 Whiskey Delta Golf, that's Charlie Suckling in the UK, and the moon in between. Now, as you can see, we're almost on the opposite side of the Earth to each other. And that means that for us to both see the moon has to be at a very low elevation. And one of the problems with 24 gigahertz is, if the moon's at low elevation, your signals are going through lots of atmosphere and lots of water vapor. And unfortunately on 24 gigs, water vapor absorbs your signal. So the longer the path you try and do, the lower the elevation, the more water vapor, and the more difficult it is. So getting world records on 24 gigs is quite difficult. In fact, Charlie and I have had about 4 or 5 attempts, and finally we were successful. Now, I guess I'll just press
down. I reckon we'll get you.
No?
Yes.
Oh, yes.
There we go.
So, some of the issues that we have to contend with. First of all, long distance, as I just explained, means high atmospheric losses. We have to choose a time of the highest elevation between both stations, and depending on the moon's declination, there can be times when we can't even see the moon at the same time, and other times it can get up to about 10 degrees at both ends, but that's about the limit. We need to choose a time when the water vapor is low at both ends. Now, water vapor is actually low when it's very cold, which means we want winter conditions, but it's very hard to get winter conditions in the UK and in Australia at the same time. So that makes it difficult. We need to choose a time when the vibration spreading of the signal is low. Now, vibration spreading is the effect that the Doppler on one side of the moon is slightly different to the Doppler shift on the other side of the moon, mainly because the Earth is rotating towards it, but its distance is slightly different from one side to the other, and so the signal gets spread up to several hundred hertz. And if your signal spreads several hundred hertz high, it's very difficult to use very narrow bandwidth modes. So we have to choose a time when the Earth is moving at about the same rate as the moon is rotating, to cancel out this effect, or at least reduce it. And we need to also choose a time when the moon is closest to the Earth. The moon goes around the Earth in an elliptical orbit, so you can pick up about 2.5 dB by choosing a time when the moon is closest to the Earth. And the other problem you have is it's very difficult to generate any sort of power at 24 gigs. And we're both running 10 watts. And to get much more than that is extremely difficult. So getting to the moon and back on 10 watts is a complication. There we go. Now Charlie, he uses a 3-metre dish. This G3 Whiskey Delta Golf.
Who I think we may have online actually, because there's Evening All Well Done Rex.
Oh.
But I'm not quite sure who.
Okay.
You might want to get Charlie to just, if he is online.
Charlie, if you are online, can you put your call sign in so we know who you are?
Yes,
Okay. So someone said good evening Rex. We think that might have been Charlie. Do we?
Yes. There's a 20-second delay, so
okay, there's
keep going.
So Charlie uses this rather large dish, which is a help, which means I don't have to use such a large dish. This is his 10-watt power amp, and even to get 10 watts, he has to phase up 2 amplifiers, and you can see the sort of trouble.
He is.
It is, Charlie, is it?
And so is G4JT.
Oh, excellent. Well, good evening, Charlie. I'm glad you're there. And Petra is there too.
Yeah, G4KGC.
Oh, terrific. Well, I'm glad the email got through.
Good stuff.
Okay, so Charlie's gone to all this effort you can see where the waveguides come in from both sides, and he's got little tuning screws which keep them all in phase. And bearing in mind that a whole wavelength at 24 gigs is only 12 millimeters, getting it perfectly phased up within a few degrees is an enormous challenge, which he's achieved. Now I operate with a much smaller dish, and the prime reason for that is I can either operate from my balcony at home, where there's not much room, or I like to go portable and open up grid squares. And a 1.14 metre dish is about as big as I can manage on my own on the roof of the car. And here's a picture up Mount Wellington. You can see it's all pretty bare and rocky. Now, as I said before, one of our big problems with these long distances, we're going through lots of atmosphere, and a 24 gigs water vapour absorbs the signal. Now, we try and pick a time when there is less water vapour, and this graph shows what's called precipitable water, and that's the amount of water vapour if you were able to precipitate it all down into water vertically above you at any time. And you can see here, at about the time we were going to attempt this QSO, precipitable water was varying from anything from 25 millimetres above us here in Tassie, down to a bit below, about 12 millimetres. Charlie, being under winter conditions, he generally had fairly low precipitable water, around 10 millimetres. Now, to give you some idea, I've put to the right of those graphs, at 20 millimetres, if the elevation was 6 degrees, that represents about 6 dB loss. And that's very hard to cope with. And that's only the loss one side, but of course if the elevation is very low at one side, it's generally a bit higher on the other side, and the loss will be lower. So you can see in this period we had to pick a time when the precipitable water was low at both ends. Around 26th of February there was a chance, but there are other reasons why that wasn't going to work. The 1st of March looked pretty good, but we were unable to arrange it at that time. And it wasn't until the 5th of March that we were able to arrange this QSO. Well, this attempt. Now, even by picking a time when the water vapour losses are low, it would be nice to get even lower. Because we've done a number of attempts and failed, and we've obviously had to improve things. Now, this graph shows the amount of precipitable water with height. You can see it was about 12 mils at sea level, and if we could have got up to 2,000 metres, it would have dropped down to about 2 mils. Now, unfortunately, we haven't got a mountain at 2,000 metres here around Hobart, but Mount Pardon?
That you can drive to.
Did I? Well, a long way from Hobart.
Yes.
But that red mark on the graph is Mount Wellington, which gets us up at 1270 metres, and that reduced the amount of precipitable water from 12 millimetres to 6 millimetres, which significantly reduces the absorption.
Is that a linear relationship between the amount of water and
It's
loss?
very close, but there's not only the water vapour loss, but there's also the oxygen loss, and oxygen's not as great, so we focus primarily on the water vapour, but it's reasonably linear. Yep. Okay. Now the next issue was to find a time when the degradation and spreading were both low. Now this graph, you can see, firstly you can see a light blue line at the bottom, and what that tells you is the dates, and it starts off at the 24th, and each little jump is a new day. So it started off on the 24th of February through to the 5th of March. Then we have a green line, which is the amount of degradation in relation to whether the moon is close to us or further away. And you can see that actually gets right down to only about 0.2 dB degradation around the 27th and 28th of February. So that would have been a terrific time to do it from this respect. And we have the purple line above, which is the amount of spreading of the signal, and you'll see it starts off at about 60 hertz at about the 28th of February, and by 5th or 6th of March it's gone up over 100 hertz. A 2-to-1 difference costs about 1 dB, so again it would be very desirable to be around the 28th of February. We'll now add a few more dimensions to this same graph, and you will see a couple of new lines. First of all, there is a red line, and that red represents the total elevation between our two stations, and what that means is it's a maximum up around the 5th of March, which means around then we will actually be able to beam higher through the atmosphere and have less absorption loss. So it is a bit higher than what it was around the 28th, which was the other option. But the more difficult problem is this black line, and the black line represents the time in minutes that we have a common window between us. And you'll notice that on the 24th of February we only had about 4 minutes between us, and round 27th and 28th we're only getting about 20 minutes between us. And to complete a QSO, when you've got to average and dig it out of the noise, you really want more time than that. And it's not until the 5th of March that we actually get those sawtooth spikes going up to about 70 minutes. So Charlie and I had to pick a compromise time between optimizing the degradation and the spreading, or optimizing the length of time we had available, which would allow us to average for a longer period. Now, in all of our failed attempts to date, we chose to optimize degradation and spreading, but this time we thought we'll compromise, give up a bit of degradation and spreading, and go for a longer time.
And that strategy worked.
And that strategy worked. Yes.
Cool.
Now, here's a graph of the total system loss on the day we chose. Not the total system loss, the system loss due to the atmosphere. The red line is Charlie's loss, which is slightly different to mine, and the reason for that is I'm down at 6 millimeters, and while he has the same attenuation, because he goes through the atmosphere at my end as well as his end, there's additional noise caused by the loss, and that noise only occurs because I'm beaming through that noisy atmosphere. And so my graph is generally lower because I've got less absorption noise, although by the time Charlie's elevation gets up to 15 or 18 degrees, mine gets down to about 2 degrees, and my absorption noise increases and his goes down, so I'm behind. So you can see from this that if we'd started when the elevation at Charlie's end was around 2 degrees, he would have had about almost 12 dB of loss, and it obviously wasn't going to work. By the time the elevation at Charlie's end got to about 6 degrees, I started to receive signals. Those little square, purple squares on the 2 dB, just now down on the 2 dB line, those little squares represent when I started to get some, and the little dots are when Charlie started to get some signal. Now, I did better than Charlie, as you could see, I should from the graph, and I was actually getting decodes without even needing to average. But he was starting to detect my signal and getting sync, and had something that he could work on and try and average. A bit later, you'll see a light blue line, and that's when the cloud came past the moon.
Water vapour.
And clouds bring water vapour in a different form. They're in drops, and they are much more lossy than the water vapour that's not in droplet form.
Okay.
And the signal for me disappeared altogether. Charlie was able to detect some small stuff because he wasn't getting the extra absorption noise from the cloud, but he was getting the attenuation from it. And then by the time signals got round 16 degrees, Charlie was able to get decodes, and I lost the cloud and I was able to get some signals. Now, we can add to these two graphs that on the previous slide another couple of graphs, which is the actual absorption system loss due to absorption if I hadn't have gone up Mount Wellington. And you can see the dashed line is worse, and it's about 2 dB worse. So the effort of going up Mount Wellington in the cold gained 2 dB. And probably was the 2 dB that made the difference. Now, what we do on 24 gigs and 10 gigs with these very weak signal EMEs, we start off sending a 1270 Hertz tone. And if you can see the yellow line here, just in the middle of the graph, you can see there's a peak on the yellow line. And that's actually been integrated over a full minute transmission of a single tone. And that's able to drag out evidence of a signal about 8 dB worse than you can actually decode a signal. So very useful for knowing that at least you're both on frequency and you've both got out of bed. And
so 8 dB worse than minus 28?
Yes.
Oh, okay.
Not quite, because you got to remember that often we don't necessarily work at minus 28 like you do on JT65C,
Yeah.
because our signal's already spread much wider in bandwidth, so we can't work at bandwidths down like 2 hertz that JT, but
Yeah.
relative.
Okay.
Relative.
Okay. About
About 8 dB. So this was the first indication I had that Charlie was transmitting. This 1270 always gives one a lot of joy. And we have a convention.
I have this picture of Rex dancing on Wellington. Anyway.
Okay. So we have a convention that is, once you've got a reasonable 1270 Hertz signal and you want the other guy to send messages, you actually send a signal at 1000 Hertz. And as soon as he sees a peak at 1000 Hertz, he swaps over. Now, all of this depends, of course, that we can be very accurate in frequency at 24 gigahertz, taking count of all the Doppler shift that's going on. But we're able to use Joe Taylor's program to derive the amount of Doppler shift, and in general get within about 20 or 30 hertz at 24 gigs of the frequencies that we're both working
It's
on.
very impressive, Rex.
Okay, we'll just go. Now I started to get some decodes from Charlie, which are here. What I've highlighted in green is the DT. Now, in order to average signals, you have to be sure that the sync is correct. You're actually averaging real signal rather than noise. And the DT is the time it takes to get the moon and back, is a very good indication that it's a real signal.
I think that's a real signal.
And so you can notice here it was 2.6, 2.6, 2.6, 2.6, 2.7, 2.6. And 2.6 is about the right time to get to the moon and back. So that gives me a lot of confidence. Then, and the purple highlighting, I've actually highlighted the difference in frequency between myself and Charlie. And you'll see that was 0, 15 hertz, minus 2 hertz, minus 18 hertz, minus 22 hertz, and 13 hertz. So essentially between the two of us, we're holding within no more than 18 hertz difference at 24 gigahertz, allowing for Doppler and everything else that's going on between us.
Two chaps on an Earth rotating. We're up here, and all these distances are changing, and all the velocities are changing.
Yes.
It's
Now, if you look down to where it has actually decoded, you will see the first time it decoded, which was 0921, 2 out of 2, it got 2 in the average, and that's the 2 above it, and it decoded Charlie's signal with his grid locator. So I had first decoded, my first one in that average was a minus 18, So in the next line I transmit both call signs and -18 as a signal report to him, that -18 dB below the noise. Then in the next line I actually got to decode in one line without needing to average. So signals were improving, and you can see for the rest of that time I got 3 out of 4 in a single line. This was at the time when I could see the moon and no clouds in the way, so things were looking good at my end.
Very.
Now unfortunately it took a long time after that. That was 9:20, and you can see by about 9:40 Charlie's starting to get good DTs and good DFs, 2.6, 2.4, 2.4, 2.5. There is a bit of variability compared to the distance of the moon. That's just because WSJT has programming things which cause errors of up to plus or minus 0.2 of a second. But hopefully on the next version Joe will tighten that up a little bit. And you can see here that Charlie finally got a decode by averaging all of those periods, and he got both call signs and -18 dB, which is what I was transmitting. About this time I'm sure Charlie and Petra both had a bit of joy. And you can see at the bottom he then started transmitting back, Roger, I've got your report, both call signs, Roger, I've got your report, and -19 being the signal strength. He picked obviously one of the signal strengths during that average. Well, -19 is about the average of the averages. Okay. Then after a while I started to see the moon again through the clouds and started to get some nice DTs, 2.6, 2.7, 2.6. And after 3 I got an average report of both call signs and R-19. So I knew Charlie had copied me. And then I start transmitting a 1500 Hertz single tone, which represents the words, represents the message RRR, Roger, 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 which concludes a normal QSO. We do exchange another tone, 1700 Hertz, which represents 73. But the QSO is complete as soon as Charlie receives RRR.
Yep.
So my conclusions: the success of this QSO is considered to be the result of, first of all, choosing a time with low precipitable water at both ends, going up Mount Wellington and saving a further 2 dB, choosing a time with the longer window and high elevations at the expense of to give more time for averaging, and less loss due to water vapour, even at the expense of higher degradation and spreading losses. And cloud is a killer. And getting no cloud at both ends, when one station's in winter and one's in summer, is not going to happen that often. Well, it'll be interesting to see if Charlie and Petra think that what I have said is what actually happened at the other end. Back to you, Justin.
At this point in time, I'll just do a call sign to keep us legal. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our ATV Experimenters Nights, and we're talking with Rex Moncur VK7MO and the half of the world record holder of the 24 gig EME contact, which was set a week ago. So yes, congratulations, Rex. So if Charlie and
Oh, there's a message.
there we go. Hang on, I will relay.
You better read it out.
I will relay. Yes, that was pretty much how it was our end. Great joy when we finally got a decode from Rex. Then tense whether he would get the R report before we ran out of window.
Yes.
So there you go. Very good indeed. Very good indeed.
Okay, thanks Charlie and thanks Petra.
Very good. So, they certainly have received that, and we have recorded that.
Okay.
You might want to let them know we have recorded the presentation, so we'll grab that off the hard disk, and I have no doubt we'll replay that at a future date. So there you go. Okay, and you're welcome. By the way, we were clear out of cloud here.
Right, yes.
So there you go. So yep, guest 713, aka Charlie and Petra. Very good indeed. So good stuff. Great stuff. Fantastic, Rex.
Okay, thank you.
Really good. Really good. It doesn't get much better than that.